Okay, where I left off, O is a linear function of the hidden units, or we're trying to introduce a response variable y sub t into the model. O is going to be a function of our hidden units, and that's going to determine our predicted distribution of y sub t. Let's actually call this p sub t, is our predicted probability at time t for each output. So the output could be another word in the neural machine translation setting. Okay, so we're going to have to choose a loss function, and a natural loss function would be the negative log likelihood then for this model, and this is going to give us the same as the cross entropy, cross entropy loss if O sub t is thought of as the logits. So this is really just the multi-class classification loss used in logistic regression. Okay, so what's going to be our model in this case? Well, we have at a given time t, we have our input, so I'm trying to draw it from bottom up, so I'll give myself some space. X sub t feeds into h sub t, also h sub t minus 1 feeds into h sub t. So this is just our basic recurrent structure. And this is our basic unit for a recurrent structure. And then h sub t feeds into O sub t, which feeds into p sub t, which maybe I'll just write this all as one thing, p sub t here. I'll just suppress the O sub t because it's just softmax activation applied to a linear fully connected layer here. And now p sub t is used to determine our loss function, L sub t. Also, our observed y sub t is used here, right? Because the loss is for y sub t. And then, now this structure is repeated, of course, so the next one, h sub t plus 1, it has x sub t plus 1 as input, which gives us p sub t plus 1, our predicted probabilities for each output word. And L sub t plus 1 is our loss function, which it takes y sub t plus 1, and so on. Okay, so these are, this is our basic recurrent neural net structure for an example where we have neural machine translation. So neural machine translation, in neural machine translation, we have our observed x sub t, which is, for example, an English word. We have our predictions, p sub t, and then we observe, of course, our French word, or our word in the other language. Let's say it's French, which is y sub t, which is our French word. And so this is how this can be thought of, is as we're just translating one word at a time. So one modification to this that was made pretty early on is bidirectional RNNs. So the issue is that these hidden units are only functions of the past observed words. You're not going to have that the future observed words are going to inform a current hidden state and thus inform our probability. And this is something we would probably want, right? So for example, the ordering of the words isn't always the same between French and English. Sometimes we put adjectives behind versus in front, and so on. And so so the ordering of the word, we don't construct sentences just from front to back. We think of the entire sentence and build it up. Right? And so a simple modification to this that was made for machine translation was bidirectional recurrent neural nets. And in the bidirectional recurrent neural nets, we're just going to have another layer of hidden states. So we have x sub t is feeding into h sub t, but then we also have some other set of hidden states, g sub t, which then goes into our prediction, p sub t. And this h sub t and g sub t both are going to be used to make this prediction. But this h sub t here, in this case, is going to feed forward to the h sub t plus 1. So you have x sub t plus 1, for example. And you have h sub t minus 1 is input to h sub t. And this is a function of x sub t minus 1 is a function of this. We're also going to have this g sub t, which is also a function of its inputs. So we have g sub t plus 1. It's also a function of its inputs. G sub t minus 1 is also a function of its inputs. But it's also going to be a function of each other, but in the opposite direction. So g sub t plus 1 is going to feed into g sub t. It's going to be input for g sub t, and so on. Right? And now both of these are, of course, used for the prediction. Right? P sub t plus 1. Okay, so you don't have that the h's are directly going to model the g's. They're not going to directly connect to the g's. It's just that we are maintaining separately a forward hidden state and a backwards hidden state. And these are both functions of the input, and they both are inputs to the predicted probability. And the remainder is the same. You have your loss function, how it responds to the predicted probability, it's the same. So we're not going to talk about that in our compute graph. And the specific functional form for g sub t is going to be the same as the h sub t. It's still going to be a tanh of the linear function of the inputs, right? And so it's still going to have the same structure as the h. The only difference is that the input directionality is reversed. Right? So that's one modification. A more complicated modification is in the LSTM. And we'll get to that, but before we get to that, let's just talk a little bit about how we can estimate, or how we can do backpropagation through time, so backpropagation using a recurrent neural net. So let's talk a bit about